everyone, my name is Clara Liberger, and so I'm passionate about sustainability subjects and how to tackle climate change today. And so I'm working on green hydrogen production, clean hydrogen production, and overall equipment in hydrogen ecosystem for several years now.
I'm Jean-Yves Tresson, working with the industrial equipment team of Dassault Systèmes, focusing on the solutions, more specifically on the power and fluidic equipment. And today, as Clara said, we are going to deep dive on the hydrogen equipment. Basically, a digital twin represents the shape of physical object in 3 dimensions, but focusing on one specific object. Whereas the virtual twin experience lets you more visualize, model, and simulate the entire environment of your equipment.
So, at first glance, an electrolyzer is a fairly simple gas machine with storage system, piping, tubing, power supply, and a compressor, for instance. But what makes today's electrolyzer complex are 2 different points. The first one will be that it has to be powered with renewable energy if we want to have what we call today green hydrogen. And also, we have the presence of the cell stack, a very complex design element. So, for the first point, the virtual twin will enable manufacturers to test and improve the reactivity of their electrolyzer to intermittent energy, solar power, wind power, for instance. Depending on the technology, alkaline, PEM, AEM, SOEC, the reaction time is not the same and can make a real difference in the clean hydrogen market today. Another environmental issue is service life, ranging from 5K to 80K hours. The great difference in the lifespan of the electrolyzer depends on the type of electrolyzer, PEM, alkaline, and so on, but also on the choice of equipment. For instance, if we are choosing materials to resist hydrogen enrichment, choosing of fittings, application of standards relating to equipment exposed to excessive pressure, installation of H2 and O2 compartments. For the second point, we go into the detail of the electrolyzer chemical application. The digital twin enables us to investigate the optimal electrode structure for gas diffusion. This is one of the prerequisites for the efficiency of your electrolyzer today. The more optimized the design, the greater the efficiency. So, the design will have to respond to precise challenges: the stability, thermal, chemical, and mechanical stability, the connectivity, the installation of your equipment, the cost-effective and economic fabrication process, and also the easy fabrication of the membrane, for instance. So, these challenges can be addressed upstream of production through virtual twin.
As you said, Clara, at the design phase, manufacturers will define the pressure and the temperature values, which are critical because, in fact, whatever they are internal or external, this will totally impact the equipment behavior and the way we are going to operate and service the equipment. And this is really important for hydrogen equipment such as the electrolyzer, because we know that the process is actually to decompose the water into the oxygen and the hydrogen gas. So we have few elements to take into consideration. And related to indicators, we are working with pressure from 12 to 20 megapascals. So this is pretty big, so let's say 120 to 100 bars. And temperature with systems operating between 100 degrees Celsius to, let's say, 850 degrees Celsius for the very high temperature electrolysis. So the designers can really optimize the equipment and work with normal, but also with unexpected conditions.
So, the hydrogen equipment maintenance will be crucial to user safety and equipment durability today. That's why it's important to start maintenance engineering early in the product development process and to design with this criterion in mind. Because the hydrogen is a very corrosive gas, maintenance is important. In particular, periodic check to monitor the state of your equipment exposed to corrosion and mechanical fatigue.
And actually, the objective to work on maintenance engineering, as you said, at an early phase, is again to optimize the equipment to make sure that we achieve a better reliability and availability of the equipment when I'm going to use it on the field. Finally, with the virtual twin of the equipment, the teams that are able to design, let's say, maintenance-friendly equipment with, for example, the field quality intelligence, the work instruction setup to make sure that the team, they know, they understand and what they are going to do with which asset or equipment, in order again to minimize the downtime and maximize performance. And again, knowing that we do that upfront at the engineering phase.
So let's take an interesting use case. So the value chain of hydrogen is pretty vast. An electrolyzer manufacturer will not always make his own cell stack, his own bipolar plate, for instance. And so he will therefore maybe call to a cell stack manufacturer, a bipolar plate manufacturer to do it. Similarly, a hydrogen producer, supplier, will not create his own electrolyzer, not always, so he will buy it from an electrolyzer manufacturer. If we take the first case, there will be an important exchange of data between the electrolyzer manufacturer and the bipolar plate manufacturer. Maybe the design proposed by the bipolar plate manufacturer will not suit my electrolyzer manufacturer, depending on the pressure capabilities, the gas diffusion capabilities, for instance, or also just the electrode surface size. So he will then propose another design depending on what he wants: pressure, surface, size, materials. My bipolar plate manufacturer will then have to check if their machines are capable of creating this new design coming from the electrolyzer manufacturer. In the second example, it is somewhat the same case actually. My hydrogen manufacturer will have to integrate the electrolyzer into its production site. In other words, linking it with piping, tubing to its on-site equipment, compressor, tank, HVAC, and so on. So for this, either he chooses a turnkey services, so he don't have to do nothing, or he chooses to integrate it himself on-site. If he integrates it himself on site, he will need to have the 2D and the 3D data from the electrolyzer manufacturer to be able to create schematic model, logical model. So there is a data exchange and there is a knowledge sharing.
With our solution, the 3D Experience platform, actually we are going to digitally connect all participants to this innovation process with a secure and real-time collaboration across all disciplines. So we are talking about engineering, manufacturing, could be finance, after sales, and also some transversal business processes, such as governance, could be requirements, change, and so on. And in fact, by sharing a common infrastructure, people will be able to work with a unique data referential and repository, so a central point of points, and all stakeholders will be able to contribute ideas, plan, and work all together. Today, anyway, there is no more only mechanical design. We talk more and more about multidisciplinary engineering with a model-based system engineering approach, because we talk about systems, not only about specific parts, components, but really systems of systems or systems. And here the objective of this approach is really to better support the concurrent execution of multiple engineering tasks, design and simulation business processes along my life cycle. And basically, this new systematic approach that includes robust integration and interoperability, because again, we talk about concurrent engineering. The intent is really to refine and enhance the current ecosystem at people, process and technology levels. And as we said, everything starts with requirements. So I'm going to define the requirements, and then I will trace all the requirements at each system level. Then to finally lower the design costs, manufacturers will work on the electrolyzer and other major component systems, but working at the architecture level. They will define the architecture. So it means that the systems will be decomposed to be then rapidly modeled, simulated and validated, and therefore will be able to speed up the development time.